Okay, we are back again doing practice CLEP calculus exams that I found on the web. Here's the link also in the description, and we are moving right along. For this practice test, we have now moved into the section where calculators are allowed, which is fantastic. And according to the exam, the calculator that they give you is basically a digital version of Texas Instruments TI-84. So I happen to have one here, very nice, so that's what we'll be using. And for the first question, it asks us for the definite integral, lower bound 5, upper bound 10, for the natural log of 10x divided by 10. What does that equal? And it's definitely going to be messy. It's definitely not anything we want to do by hand. So we're going to go into our graph plots, y equals button, and we're going to punch in that equation. We're going to take the natural log of 10 times x divided by x. And then we are going to go to the graph screen, and it's going to draw it out for us. And then you go to the calc menu. So we'd say second and hit the button to get to the calc menu. And you go down to the integral. You see the integral sign, f of x dx. So that's going to ask us to do definite integral. And it's going to ask us for the lower limit, so you can arrow key over to it if you want. With the zoom setting right now, the pixel widths are not an even number. You can set it so that it is. There's an easy way to do that, and I might show you that later. But you can also just type it in. We can hit 5 and hit enter, and it accepts that, and you don't even need to worry about doing the arrow keys back and forth. So it asks us also what's the upper limit. We're going to say 10, and it's going to think about it for a little while, and it's going to say 2.9518. And in fact, 2.952 is one of the answers right there. So that is correct, selection B. And boy, isn't that easy when we can use a calculator. All right. The next one here. The graph of the function is given above. What is the limit as x approaches 2 for x over this function plus 1? So boy, that's an odd way of doing it, isn't it? But if we consider this, we know that the point at x equals 2, that the function is -1. So what would this normally be? It would be x equals to 2 over f of 2 -1 plus 1, which equals to 2 over 0. And yes, that's a divide by 0 error, but there's kind of two things that can happen to a graph when you're dividing by 0. One, it's either going to have a gap in it, or the other thing that can happen is an asymptote. If you just do y equals 1 over x at 0, you can see an asymptote. It zooms up to infinity and then comes back up from -infinity. So given the options here, we can take a pretty safe guess that is going to be infinity there. And actually, I can whip it faster to do it this way than on the calculator, but since I do have the calculator, I'll just show you a quick proof here. And so I've jotted into the calculator, and this we basically recognize this as a cosine function, especially because at x equals 0, it equals 1. But we would normally expect it to be at -1, where x equals pi, but x equals 2 instead of pi, so we have to turn that 2 into a pi. by taking the x divided by 2 times pi, and then for the y2 here, I've put in this guy, x over the original function plus 1. So we can go to the graph screen. I already have it done out. And if I go over to x equals 2, you can see it's right there at the bottom, and you can see that the other function right there, it is zooming up to infinity and then coming back down from infinity, and then it every time this goes to -1 and zooms back up to infinity. So that's what's happening there, but we can determine that pretty quickly without the calculator. It's almost not worth using the calculator for that one. So moving on then, number 38. So it asks us, let f be a continuous function, capital F. The graph of the derivative of whatever that is given above. And I think there's something wrong with this diagram because there's just no graph there. All it really shows us is these two empty dots connected by a dotted line, and that implies to me that there's supposed to be some function coming into one of those dots, and then the graph jumps to the other one and continues on from there. So you have some kind of, not just a gap at x equals 2, but a complete discontinuity in whatever function there is. And I think that's the kind of notation you would use to do that. It's just somewhere in the translation from the original to this version of the document, part of the picture got lost, or I don't know, whatever happened. But the options being, which of the following statements is false? That the original function at 2 minus the original function at 0 is greater than 0, or f is defined at x equals 2, or f is differentiable at x equals 2, or f has a maximum at x equals 2, or f is decreasing from 2 onwards, that f is decreasing and has a negative slope. And again, it's really hard to tell what they're going for when there isn't a proper picture of it. But we can say for absolutely certain that if this is the graph of the derivative and something very bad happens at x equals 2, it is the derivative, a proper derivative certainly does not exist here. This is the graph of the derivative, and at x equals 2, something happens that is not continuous. So we can take a safe guess that we're talking f is definitely not differentiable at that value, x equals 2. So C is going to be false, and all the other ones, your guess is as good as mine. I can't prove that those are true because there's not enough information. But the C is definitely the one that we can pick out as being most certainly false in this situation. All right, number 39. Let f be a function where the second derivative is sine of 2x minus the cosine of 4x. How many points of inflection does the graph of f have on the interval? So we're basically asking, remember that points of inflection is where the second derivative is 0. We're given the second derivative, so we just need to count how many times, not just where it equals 0, but where it changes sign, where it changes from positive to negative or negative to positive. So not just where it's 0, but where it actually has to cross the x-axis. If it comes down and touches the x-axis and then goes back the other way, that's not an inflection point. It actually has to cross. So we can pull out our calculator again, and we're going to take that sine of 2x minus the cosine of 4x And we are going to graph that. And let me show you a quick trick here. So pardon the pause of the video. This is, if it's just the standard default zoom setting of the screen, it gets sloppy, it gets hard to look at. If you do the trace and go this way, you're not even gonna make it out to 10. It's only gonna get to, what does it get to? You know, it gets to 10 there. So you could kind of try to look at it there, but it's not the best. So if we go to zoom, and we can go down to zoom integer, and center it on 0. And it helps to set up the window before you put the graph in, so it doesn't have to redraw it every time. But now we're going to zoom in on the same place. So it zooms in, and you can see it a little bit better there. But then I'm also going to go to window. Well, okay, it's going from -11. So we can actually kind of see it pretty well here. That get to here that 10 is here. We want the interval from 0 to 10. Maybe still a little hard to see. Yeah, at 0, it's -1. We're going to zoom in again. See if I can zoom in at 5. Let's see what that does. I don't think that worked. It just kind of recentered it. Okay, wait a minute. What did I really want to do? I'm gonna do hold on. Let me reset this here. Okay, actually the nicest way to do this, because we know we're only interested in 0 to 10, let's set the width of the screen to just beyond that. So we're going to manually set it from 1 to 11. And then when we go to the graph, we are zoomed in as much as possible nicely. Well, the individual widths of the pixels are not exactly nice values, but that's not super relevant to us. All we know that that's 0 and 10 is going to be right around there. That tick mark is the 10. So we just want to count how many times does it cross. So it crosses there, that's 1. It crosses there, that's 2. It goes to 0 but does not count, does not cross. So 3, 4 goes to 0 but does not cross, so that does not count. So here's 5, here's 6, doesn't cross again. There's 7, there's 8. So it, well, no, that's not 8 because that's beyond 10, right? That's 10 there. We stop right there. That one's outside the bounds. So only got to 7. 1, 2, 3, 4, 5, 6, 7. Don't just count what's on the screen. Make sure you're saying. We can even do that. We can just say 0 and 10 if we want to not trip ourselves up. And make sure that we're only looking at that interval. And then that's a little more clear. 1, 2, 3, 4, 5. 1, 2, 3. What happened to the other one? Not 1. See, I did that wrong. It's supposed to be 0. 0 to 10. Right? 1, 2, 3, 4, 5, 6, 7. Still 7. Okay. That's the most sure way of making sure you count it right, is to just put it in the interval that you're interested in. It is 7, and that is the correct answer. So now we're asking, the area of the region in the first quadrant, and by first quadrant we just mean the positive corner where x is positive and y is positive, the upper right of the graph. So the area in the region in the first quadrant between the graph y equals x square root of 4 minus x squared and the x-axis. So this is basically just a definite integral. It's asking us a definite integral. So we're going to jump back in to the y equals screen, and we're going to punch that in. X square root. What is the square root? Second function of this key is square root of 4 minus x squared. And then we can graph that. And, look at that little thing. That's a little goofy. So we can safely assume that it cuts off at x equals 0 because that's, or x equals 2, because that's where 2 squared makes 4. 4 minus 4 is 0. Anything greater than 2, you're going to get a negative number inside the square root, and that turns into imaginary numbers, which doesn't graph properly. So it's going to cut off at 2. And, well, we could zoom in and prove that to ourselves. We don't really need to do that. All we need to know is that in the first quadrant, the lower bound is going to be at 0 because that's where it crosses the x-axis. And then over at 2, it meets the, let's just go ahead and prove that. Let's go back to the to that zoom integer. And it's very, very small. But if we zoom in, now we can see it a little more nicely. Didn't need to do that in order to do what we're going to do next, which is just that definite integral again. So we go to the calc menu there, go to that integral, and we know the lower limit is 0, and the upper limit, because I set a zoom to a nice value, I can just arrow over to it, or I could just type it in. But the upper limit is 2. And it'll say 2.666. And, none of the answers are in decimals, but 2.6, never mind the rounding error there. It looks like 2 2/3, right? 2 2/3, and as an improper fraction, 2 2/3, that's going to be 8/3. 2 is 6/3. 6 plus 2 is 8 on top. So 8/3 is the answer. And like I said, the calculator is just kind of internally approximating So it's not uncommon for the last few digits to, you call it rounding error because that's where it comes from, where a little bit of rounding internally throws it off. But that's close enough to 2 2/3 that based on the options here, we know that's what it is. And if you really wanted to check, you could punch in, 2 square roots of 2 and 2 square roots of 3, 2/3 square roots of 2, and you would notice that those answers are do not match this as well as 8/3 does. And that is indeed the answer for number 40. Okay, that is it for that video. See you in the next one.